Okay, sorry for the delay. A little bit of technical difficulties, but ready to go. And lecture on molecular. This is titled Molecular Structure. This is basically sections 1.7 and 1.8. Molecular structure. So initially we want to talk about molecular shape. We want to talk about bond length and bond angle. So bond length. The periodic table, bond length, the periodic table is going to be a guide for several principles, okay? And we'll see different trends, and there's a lot that goes into this, and we won't necessarily go into all the details of why, but we want to learn the trends. Okay, so for bond length, the trend is that bond lengths increase to the left and down the table. This is the periodic table. Okay. And there's reasons for that. It has to do with effective nuclear charge and the atomic radius. Essentially, we're going to memorize these trends or learn these trends. And so we don't want to memorize the numbers, but I'm going to give you some numbers. Okay, so let's show some examples here. One second. So we'll be looking at these trends. We'll look at carbon, nitrogen, oxygen, and fluorine later. So let's do that now. Get used to that. Reinforcing our memorization of of row 2. So you got a CH bond. That's going to be 1.09 angstroms. You have an NH bond with a lone pair. Oops, it's just a bond. We're looking at the hydrogen bond to these atoms. 1.01 angstroms. We have an OH bond that is 0.96 angstroms. Sometimes you'll see picometers. Angstroms are common. I want you to remember that bonds are about an angstrom. Okay, we'll see some other ones later. But 1 angstrom is 10 to the minus 10 meters. So you'll see picometers as well. And then fluorine hydrogen bond is 0.92 angstroms. Okay. So, the trend is as we go from right to left, the bond length is increasing bond length. And that's going to be the opposite of electronegativity. Okay. And we'll kind of, we'll talk about electronegativity soon. The more electronegative atom is the opposite direction. Okay, so because those electrons are held closer to the nucleus, that because the more electronegative fluorine, for example, electrons are held closer to the nucleus, and that draws the H ever so closer. Okay, that's kind of a good way to think about it. And we can go down this list now and look at Cl. I'm going to leave off the lone pairs. There's 3 lone pairs on all of these. Cl, Br, and I, H. And if you look at these numbers, it's 1.27 angstroms, 1.41 angstroms, and 1.61 angstroms. And we'll see again, the size of the atom is getting larger. Okay. And so that bond is going to get longer. Okay, so we want to learn bond length trends and keep those in mind. I'd say bond length trends are far less important than bond angle. Okay, so out of the 2, bond length and bond angle, we really want to understand bond angle. Shape is going to matter a whole lot more than bond length. Bond angle is the term groups. Let me give you a definition of a group. A group is an atom or group of atoms. We'll see that as we go. Some sort of atom or group of atoms or lone pairs, but not multiple bonds. And we'll see this as we talk about this more. We just don't count multiple bonds in terms of shape. Okay, we use VSEPR, sometimes referred to as VSEPR, valence shell electron pair repulsion. Okay, so we're going to use this as our guiding principle that electron pairs are going to repulse. So valence shell electron pair repulsion. You're not going to be asked to memorize that. It's just a principle that's going to guide us. So more stable is the farther groups are apart, the more stable something is going to be. I think this is pretty intuitive. Electrons have negative charge; they're going to repel. So let's look at a list. We're going to look at 3 different shapes essentially. Number of groups. You can have 2, 3. Geometry. 2, I think, makes sense. The shortest distance between 2 points is a line. So 2 groups is going to be linear. 3 groups, imagine the shape of 3 points is going to be 3 points equidistant from each other is going to be a triangle. We call it trigonal. And the 4 groups is where it gets tricky. If you're in one plane, 4 points equidistant from each other or something like that would be a square. Okay, so we would call it square planar, but it's not. These 4 groups are going to orient themselves as far away as possible, and that's going to be tetrahedral. We'll spend quite a bit of time talking about tetrahedral. And then finally, the bond angle that corresponds to each of these shapes is 180 degrees, 120 degrees, and 109.5. These numbers should become, essentially become memorized. 109.5 is a number you should tuck away. And this is 3D. Okay, that's really important. So let's start with linear. Draw some linear shapes. Start with a carbon-carbon triple bond. We drew this Lewis structure earlier. Again, we're drawing Lewis structures. We're going to look at shape, and then we're going to dive deeper and look at hybridization. Okay, so we're going to sort of ignore the multiple bonds in terms of shape. We're not going to ignore them in terms of hybridization, but we'll get to that. Each carbon, though, has 2 groups attached. This carbon 1, carbon 2. Carbon 1 is attached to a hydrogen and is attached to carbon 2. Carbon 2 is attached to a hydrogen and attached to carbon 1. So it's attached to 2 groups, so this is linear. The bond angle here is just how we've drawn it. This is 180 degrees as well as, and so is the other one. We will revisit a lot of these things as we get into hybridization. So now we're given some examples. Okay, so that's an example of linear. There are certainly others. Let's introduce this one, HBeH2. There's some empty orbitals on there that we'll talk about later, but there are two groups. There's two hydrogens on beryllium. Beryllium only has two valence electrons. It can only form two bonds. So this angle is 180 degrees. Okay, so let's look at trigonal. Planar, we call this. It's in a plane. It's three groups. Trigonal planar. Let's look at another Lewis structure that we drew earlier. See, we're sort of, our Lewis structures are going to get more and more sophisticated. Again, we sort of ignore the multiple bonds, so these bond angles are 120 degrees all around. If you look at carbon 1 and carbon 2, focus on carbon 1. There's two hydrogens and another carbon attached, so there's three groups. They are all as far away apart as possible, 120 degrees. Each carbon is trigonal planar. That's important, okay? Trigonal planar, each one. Let's look at a single atom, boron. Again, all these angles are 120 degrees. Okay. There's several more we could look at, but we can move on from that. I want to spend some time on tetrahedral shape. Tetrahedral. So again, let's look at methane. The Lewis structure for methane. Not drawn perfectly there, but this would be considered square planar. If all the hydrogens were in one plane, then it would be square planar, and all these angles would be 90 degrees, perfectly equal apart, right? Again, not drawn perfectly, but the reality is 90 degrees doesn't. Carbon and hydrogen with electrons, those electrons are all going to repulse each other. So all four bonds are going to repulse, and we want to get them as far away as possible. The really beautiful way this plays out is carbon is what we call tetrahedral. The way to understand this is to simply make a model. You need to get a model kit. You need to put 4 hydrogens around a carbon. It'll take you 2 minutes or less. And the hydrogens, if we connected these, then this would form the points of a tetrahedron. Okay, it's like a pyramid, but all sides, all the 4 triangles are all perfectly identical in size. Okay, so it's a tetrahedron. You can Google tetrahedron. You can look at shapes. There's examples in the book that show this in 3 dimensions pretty nicely. And you can take a look at those. Okay, so this is the preferred geometry. We use what's called a dash and a wedge. Oops. And a wedge. This is a wedge. It's coming out towards you. That's what that means. These lines here is a dash. It means it's going back. We'll talk about this in class. We'll bring some model kits in. And this is a very, very, very important concept, the 3-dimensionality of carbon. Okay, solid lines, bonds are in a plane, and all these angles here are 109.5 degrees. Okay, every single angle is perfectly identical when you have 4 identical groups. Okay, so even this angle here that looks like these are really close is 109.5. It's impossible to perfectly draw things that are 3-dimensional in 2-dimensional space. So you got to see 3D. All right. The wedges and the dashes are very, very significant. So this can tumble in space. I'll use that term a lot. It can tumble around in space. That's important to recognize. So there's multiple ways you can draw this. The one I've shown there, you can put the bonds in the plane like this. That's appropriate. Again, what we're saying is actually this hydrogen A is directly in front of B. If you looked at it at a certain angle, they would eclipse. The hydrogen A would be in front of B, okay? And the best way to show it is to have the wedge kind of coming out like this rather than the dash kind of where I'm circling, okay? That's kind of a bit of a nitpicky thing, but still. Now, again, this can kind of tumble in space. So if this, say this molecule kind of tumbled this way, you'd get something like this. Give or take. We're not worried about A and B, but that's the point, is you could draw it that way. You could flip it 180 degrees and draw it another way. Now, notice the bonds in the plane, the solid lines, are always adjacent. Those aren't wedges. Those are just the solid lines. They're adjacent. This is incorrect. Okay, that's actually square planar is the way that would really be. Those solid lines are 180 degrees apart. That's incorrect. You got to learn how to draw these. Okay. You know, another variation of that is something like this. Incorrect. Okay, so you have to learn how to draw these in 3 dimensions. So that's carbon. That's 3-dimensional. Okay, let's look at ammonia and water. Very important molecules. It's important for you to recognize that if I gave you NH3, for example, you'd probably come up with a Lewis structure that looked like this. This would be a correct Lewis structure. However, this ammonia is not planar. Just like methane with 4 groups is not planar, ammonia with 4 groups is not planar. Remember, this lone pair is a group. The sooner you get used to the number of electron pairs around these atoms in row 2, the sooner you're going to be comfortable. And that pair of electrons is a group, and you got 3 hydrogens. So what's it look like? We're going to draw it in 3 dimensions. This hydrogen-nitrogen bond and the pair of electrons are in the same plane, and then we're going to use wedge and dash to draw the hydrogens that are out of the plane. One's back and one's forward. Okay, we technically call this trigonal pyramidal. That doesn't matter. Okay, it's not trigonal planar. It is not planar. It's actually tetrahedral, essentially, at nitrogen. But the terminology used is trigonal pyramidal. Okay, it's more like a pyramid, and that's just because the electrons are different than a hydrogen. The lone pair is different than hydrogens. So it's one of 4 groups, but they're different. So there's some distortion. Okay, if we looked at the bond angles, it'd be like 107 for these hydrogens, I believe. Okay, so just a little bit of distortion. You don't need to know that. Okay, but not planar, not trigonal planar. And as we'll see later, there is an orbital here. Okay, and we'll talk about that later. Okay, we're going to talk about hybridization, but just to glimpse ahead. There's an orbital that pair of electrons is in. All these and hydrogen bonds have orbitals too. Okay, I just want to continue to give you deeper glimpses of reality, but that's enough of that for now. And then water, if I gave you water, you'd come up with a Lewis structure that looked like this. You'd have 2 lone pairs on oxygen after you accounted for all of them, and you'd say there's water. And that'd be a correct Lewis structure, but it is not planar. It's tetrahedral at oxygen. Okay. The way it's typically drawn, and this is acceptable if I ask you to draw water, is we call it bent. Okay. A better way to represent this, to remind us of the tetrahedral nature, is similar to what we just drew for ammonia. Okay, it looks a little funny, but this bond angle now is 105 degrees. Still more distortion. We call it bent, but for all intents and purposes, this is tetrahedral. We're going to use a term called sp3 hybridized when we get to hybridization. Again, there's orbitals here. Okay, but that's enough. That's enough for our purposes now. Okay, ammonia, water, and methane are all very similar in shape, and in fact, you could do the same thing for HF. Okay, so do the same thing. Take home, same exercise. Draw the Lewis structure and then draw it in 3 dimensions. Okay, this is very, very important for stereochemistry. So we're setting the stage for what is chapter 5. So it seems like a long way off, but we're setting the stage for stereochemistry. Okay. All right, so that's a bit about molecular shape. Again, we'll kind of come back to it in different ways. Let's go on to 1.8, and that is drawing organic structures. Okay, so we showed methane, a carbon with 4 hydrogens around it, but you can have thousands of carbons connected. Okay, and we're going to have to draw condensed structures. So let's draw a butane molecule. We'll get to naming later. Butane stands for 4, but we're going to put 4 carbons in a row. And so let's say I gave you C4H10. Oops, H10. C4H10 as a Lewis structure problem. Again, you'll get to the point where you're drawing these in your sleep. You put 4 carbons, and every carbon has to have 4 bonds. And you're going to start filling in hydrogens. Okay, so this would be the structure for butane. And you would draw that out, and eventually it gets out of hand. Okay, you start drawing things, and it gets obnoxious. And so we have things called condensed structures, and eventually we'll get to skeletal structures. But this is equivalent to here. That's called a condensed structure. This was a Lewis structure here. This is a formula up here. This is a Lewis structure, and this is a condensed structure. Okay, when you start having more and more CH2s in between, you can condense it even further and do this. The number of CH2s, you can have parentheses to do that. Okay, you should go through the book and kind of learn this. So that's butane is the name of it. And let me draw another one as a reminder of isomers, or an introduction to isomers, sorry. Again, we're going to kind of keep coming around the same themes over and over in different ways. So now we can connect 4 carbons. C4H10 can also look like this. If you count them up, you got 4 carbons and you got 10 hydrogens. This is also C4H10. These two are constitutional isomers of one another. Okay? We can draw a condensed structure that looks like this. You have 3 CH3s, 1, 2, and 3, around a central carbon. You can just put a C there, actually, and an H. Okay, so there's some formulas that are implicit there. Okay. Let's do a couple more organic structures with oxygens in them. We can draw what's called an aldehyde. Again, this will be an introduction to functional groups. So there's a Lewis structure there, condensed structure. Okay, that's gonna look weird at first, that's CHO, but it has to be equal to that, because carbon has to have 4 bonds, hydrogen can only form 1 bond, oxygen can form 2 bonds very easily, so on and so forth. So that means that there's a bond here in between the CH2 and the CH, or the CHO. Okay, so you got to kind of work through these. Let's do another one. This is called an ether. This was an aldehyde. This is an ether. And this is equivalent to CH3O, CH3. You have 2 CH3s that are bound to an oxygen. There's 2 lone pairs there. Okay. In the condensed structure, you don't need lone pairs. They're implied. You'll see that a lot. There'll be a lot of implied lone pairs. Just to see a few more structures, or actually, let me do this for you. Let me give you the drawn out structure, and you can work on the condensed. That's a carbon. That's an oxygen. That's an OH. Okay, so you draw the condensed. Same thing here. Two lone pairs up here. Draw the condensed form. Okay, so a couple take-home assignments. Okay, now let's further take this and look at skeletal structures. Okay, skeletal, just like it sounds, it's kind of a bare bones structure. Okay, so we're going to assume carbonate junctions. You'll see what I mean, and you'll assume implicit hydrogens. We'll use that term implicit a lot. There'll be implicit lone pairs and implicit hydrogens. They have to be there based on the nature of the atom. Let's show an example. This is hexane, hex for 6, like a hexagon. Let's draw this out. So if I gave you C6H14, you would need to draw out, this is one of them. We'll talk about isomers more later when we get into alkanes. but you might draw this. This is called normal or N-hexane. And you can see really quickly, start drawing these out, and you can see that it gets old pretty fast. Okay, so you got 6 carbons, you got 14 hydrogens. Again, they have to be there. If there's only 6 carbons, you got to fill it up with something. You got to fill it with hydrogens. Okay, so the skeletal is simply this. Count your carbons there. Every single junction or turn is a carbon, so we can label them 1, 2, 3, 4, 5, 6. Okay, so this is not a condensed structure. Let's draw what that would be. CH3, CH2, 4 of them now, CH3. That'd be the condensed. This is the skeletal. These are the same thing. Okay, they mean the same thing. So skeletal are going to be by and large what we'll use a lot. Okay, and notice carbon 1 and carbon 6. You've got a carbon there, and the end of a chain implies a CH3. So let's number these: 1, 2, 3, 4, 5, and 6. So 1 and 6 have methyls. We call those methyl groups. 2 through 5 are called methylenes. We'll get to that with alkanes later. Okay. Now let's look at a ring. Okay. This would be called hexane. This, sorry. Let's draw now carbons in a ring. We'll see lots of rings. This is actually C6H12. Now we've got a carbon-carbon bond we got an extra carbon-carbon bond in the ring. So we have 1 through 6, and now there's just CH2s all the way around. These H2s are like so. You could put wedges and dashes in there if you wanted to kind of show that three-dimensionality. Okay, it's always there. But skeletal is simply a hexagon. Cyclohexane is a hexagon. You'll get very good at drawing these. Cyclohexane. Okay. So now let me do the opposite. Let me give you a few skeletal structures. When we have oxygen or nitrogen, we got to include those. Okay. So let me draw a couple skeletals, and you can draw them out. I'm going to leave off implied hydrogens and implied lone pairs. Now I want you to draw the full drawn out structure of both of these. Okay. Draw out all the hydrogens, all the lone pairs. Again, all this stuff is practice. Okay. One more thing for drawing these structures, we want to take into account charge. Remember we talked about formal charge? We need to take that into account in our skeletal structures. So a plus or a minus charge essentially takes the place of one hydrogen. Takes place of hydrogen or something else. Okay. Meaning if you've got a plus charge on a carbon, you can only have 3 bonds. If you've got a pair of electrons on a carbon, then you can only have 3 other bonds. Okay, so let's show these. Okay, plus charge has no lone pairs, right? We've taken an electron away. A negative charge has it has a lone pair. It's got an extra electron. So let's show both examples. That plus charge on that carbon, there's a hydrogen that's implied. Okay, you'll get used to seeing the implied hydrogens. You need to draw them out over and over and over until you see them in your sleep. Those are the exact same things. Okay. By definition, the plus charge on the right, let's call it A. By definition, the plus charge means that there's a hydrogen there. Okay. Of course, there's 2 hydrogens on every other one of these carbons as well. Okay. I'll try to draw them from time to time to continue to remind you, but same idea here. This means that there's a hydrogen there. Okay. Again, now go through each of these and calculate the formal charge. Convince yourself that you understand, I'm going to write that word there, that you understand this concept, all these concepts. Okay. Hydrogens are implicit. Lone pairs can be implicit for like heteroatoms and things like that. Obviously, we have to show this lone pair cannot be implicit because it's charged. Essentially, charged species, lone pairs must be explicitly drawn. Okay, and we'll talk about that more when we get to, we'll talk about that more. But that wraps up the lecture on molecular structure. And we have 2 more lectures in chapter 1, hybridization and electronegativity, and we'll continue on with those shortly.